Hello, everyone. I'm Wang Xiaohang. This talk is about deep arbitrary scale image superresolution via scale-equivariance pursuit. Our goal in this work is arbitrary scale superresolution, which aims to use a single model to achieve image upsampling at any real-valued scaling factor. The key idea of our works are as follows. First, explicitly inject the scale information into the backbone network to make the network adaptively modify the extracted features according to the requirements of upsampling. Second, inspired by Kriging interpolation, we split the upsampler into scale-independent and scale-dependent components to endow the network with equivariance, which further improve the model's performance on scales that were unseen during training. Third, our data processing approach for arbitrary scale superresolution enables more straightforward online large-scale pre-training and offers greater flexibility in selecting network layers. Here, we introduce our motivations. It is evident that arbitrary scale superresolution surpasses fixed scale methods in terms of resource consumption and flexibility. However, for a single model, its exposure to scaling factors during training is limited. When deployment, it's common to encounter scales that were never seen during training. Meanwhile, we observe that for the same image, the features used for upsampling at different scaling factors are not entirely identical. Therefore, we revisited our task and argue that when the scaling factor changes, the network should adapt accordingly in a rule-based manner, namely, scale-equivariance. We will introduce our method from the following 5 aspects. The first problem: how do we achieve arbitrary resolution upsampling? We follow the work of LIIF and LTE, constructing an implicit field for the input image and reconstructing high-resolution results by querying the RGB values at the target coordinates. Due to the arbitrary nature of the queried coordinates' positions and quantity, it allows for achieving arbitrary resolution output. However, our implicit field differs from previous works. We'll elaborate on that later. The second problem: how to incorporate scale information during the feature extraction process. We design a pluggable transformer-style information injector named Adaptive Feature Extractor to enhance the equivariance of the backbone. The input scale factor is expanded to a higher dimension by sine-cosine encoding, which is further mapped to a latent space to carry scale information by a linear layer. Then this scale vector is modulated with the kernel basis convolution layer, forming a scale-interpolated adaptive convolutional kernel for feature encoding. By applying the adaptive feature extractor to each transformer group of the backbone network, the scale information permeates the entire feature extraction process. The third problem: how to enhance the equivariance of the upsampling operator. From the perspective of Kriging interpolation, the upsampling process can be decomposed into 2 parts, the data kernel and the scale kernel. The data kernel is independent of the upsampling process and mainly learns the prior distribution from known observed data. The scale kernel is strongly related to the sampling scales. Inspired by this, we design a learnable scale-adaptive upsampler for a scissor named Neural Kriging Upsampler. It has 2 collaborating branches. The first branch is a scale-insensitive branch that uses SE blocks to explore the prior relationship between image feature values and spatial location learned from the training data, yielding data kernels. The other branch is scale-sensitive, which conducts relative position encoding on sampling points with reference to the target coordinates, calculating the spatial geometric relationship through RBF function to obtain the scale kernels according to the target scale. We also cascade the RBF function with a MLP to enhance the learning ability. The fourth problem: how to train an arbitrary scale model. To enable training with different image sizes and avoid bias towards fixed scale as in ARB-SR, we propose a new data processing method to encourage a more general training scale coverage. We first downscale HR images to 48 by 48 pixels, forming stacked input batches. After backbone feature extraction, only target regions are upsampled to HR by the learned-to-scissor model, together with the corresponding regions from the ground truth HR images, forming L1 loss training pairs. In this way, we avoid the inconvenience caused by inputs of different scales. Compared to the method of constructing coordinate RGB pairs used in LIIF, our approach allows for the complete prediction of the image at once, eliminating the limitations of the implicit field on MLP networks. This greatly enhances the flexibility of the model architecture. The fifth problem: how to measure equivariance. Mathematically, operator G is completely equivariant to operation T if the formula Gt equals Tg is satisfied. Thus, we propose the measurement, which is defined as the PSNR between two sets of images, obtained by swapping the order of upsampling and downsampling, as the metric of scale equivariance. The calculation can be formulated as equation 6. This is the overall structure of our model. It consists of three parts: the head, the AFE groups, and the neural Kriging upsampler. The head is one layer of convolution that extracts shallow features and enriches low-level patterns. The main body of the backbone contains a series of AFE groups to achieve a scale-adaptive feature extraction and gain a large receptive field. The AFE group is composed of an AFE block, several window-based self-attention, a global self-attention, and a 3x3 convolution. The last part is our proposed neural Kriging upsampler. We next present some experimental results to demonstrate the effectiveness of our approach. This figure shows comparisons on Urban 100 dataset. We observe that our method has significant advantages in restoring patterns such as repeated textures, edges of cross grids, and other high-frequency dense details which are sensitive to scale changes. However, previous methods often damage these repeated structures. This image shows the visual comparison results on the Mongo 109 dataset. It can be observed that our model is able to restore more clear edges for printed texts at different scales, such as the letters E, A, P, R, and so on. This is the table for quantitative comparison with previous SOTAs. Our model outperforms previous SOTA approaches at almost all real number scales on all datasets, showing the superiority of our proposed scale-equivariant model. This image visualizes the results of the scale vectors and Kriging kernels. In Figure A, we also calculate the cosine similarity for analysis. We observe that, first, even if the scale changes lightly, the scale vectors are different. Second, as the scale increases, the scale-dependent kernel change gradually. Third, cases with closer scales have more similar scale vectors. All of these findings validate our approach to achieving equivariance. That's all, thank you for watching.